Yes, sir. I can choose the work energy power.
Okay, so today we are going to start this topic. And so the first topic obviously is work. First, we'll talk about work. So in physics, you have to understand work is defined in a different way. So in our day-to-day life, any type of physical or mental activity we call as work. But in case of physics, we say that a work is done when force acts on a body and displaces it in the direction of the force. Now, to be more precise mathematically, work is defined as the dot product of force vector and displacement vector. Now, here you have to understand that when we say work, who is doing this work? So, work is always done by some force. For example, suppose if this is a horizontal surface and on this surface a block is kept, and if net force on this block is zero and the block is either moving or is at rest, if net force is zero, then no work is done. Total work done is zero. So work is said to be done when a force acts on a body. So here, let's say some F force is acting on this body. Force is a vector in a particular direction, and is displacement. Body is getting displaced in a particular direction. Okay. So now, for example, suppose in this case, because the body block is placed on a surface, so the block is sliding on the surface with the help of this, and this force is acting on it. Now, in this situation, you can see that after some time, the block will recover a displacement and will reach somewhat here. Let's say here, it reaches here. Okay, so this is the displacement vector of this block. This is the displacement vector, which is in a particular direction. You can see. So this is displacement vector, and
Yes,
this
sir.
is force vector, and this is the here angle between the displacement vector and the force vector. Let's call this angle as theta. Now work is simply defined as the dot product of force vector and displacement vector. That is the mathematical correct definition of the force. Now you already know dot product of two vector from the vector chapter, right? How
Yes,
we take
sir.
dot product of two vectors. Okay. And you know that whenever we take dot product of two vectors, the result that we get is a scalar quantity. So from here, you should also understand that, okay, when we take dot product of force vector and displacement vector, the result that I will get is work, and it will be a scalar quantity. So work is a scalar quantity. Here you can see that it is dot product of force vector and displacement vector. Now, if you see here, then it will become FD cos theta. Now, FD cos theta can also be written as F cos theta into D, right? Where you can
Yes,
see F cos theta is that component of force which is in the direction of the displacement. So you can also express the work as force multiplied with component of displacement multiplied with component of force along the displacement. Displacement multiplied with component of force along the displacement. Can you see here written? But it
yes,
can
sir.
also be expressed as F into d cos theta. So you can also say that the work is force multiplied with component of displacement along the force.
Yes, sir. We can say.
So simply it is simply dot product of the two vector. Okay. Now here comes a very important thing that right now whatever we discuss, this is true for a work done by a constant force. If suppose the force is changing, then definitely when you will take dot product of force and displacement, which value of force you will substitute? Because the forces have different value of different time. Are you getting? In case of variable force, if the force is varying, when I say variable force, you should understand variable force. So force may be variable if if the magnitude of force is changing or direction of the force vector is changing or both is changing. Are you getting?
Getting, sir. And
Now, when the force is variable, in that situation, what you can do is you can find the work done for a very small displacement. For example, suppose if there is a particle, let's say this is the particle, and some force is acting, and the force is variable. Okay, force is, let's say, a function of time or a function of displacement, anything like that. It is variable. Force is some function of time or anything. So here, if the force is variable, then definitely for the entire total displacement, this is, we don't have a particular value of force. At different small displacement, the force will have different value because force is continuously changing. Suppose particle starts from here and goes up to here. Okay, so definitely this is the total displacement of the particle, but this total displacement can be broken as a series of small displacements, right? A small dx displacement, if you add, then you will get the total displacement. And in each dx displacement, if you see, then the force will be different because the force is variable. So for the entire displacement, this is the total displacement, this yellow vector. So for the entire displacement, force is not having the same value. That's why we cannot directly find the work by taking dot product of the force and total displacement. We cannot take dot product with the total displacement. Are you getting? What we can do is we can assume that at any particular instant, the force acting on it is, let's say, f vector, which is variable. And at that time, let's assume that in a dt time, the body, there is a small displacement, dx displacement. So then during that small dt time, the work done by the force can be written as dot product of the force vector and the displacement vector. So f dot dr I am writing because dr we use for general 2D, 3D displacement. It is not
so,
necessary. Yeah.
so I mean, in that small displacement, we consider force as a constant thing. So,
Yeah, so during that small displacement, because the displacement is infinitesimally small in a very infinitesimally small interval of time, so during that interval, we consider that the variation in force is there, but the variation is very small because the time interval is very small. So, and the displacement is very small. So if the force is a function of time or displacement, the force is varying, but it is for to vary, you know, some time is required and time is very small. So the variation during that dt time is negligible and we can consider that, okay, during that small, it is constant. And then we can integrate it from r1 to R2, let's say final position vector becomes R2, and then you will get the total work done. So total work done will be simply the integration of all small work done, right? Understood?
it's understood.
Okay. So again, I'm adding this here. You can see this is written here, work done by the variable force. Let's go to the next. In the same way, you can take an example of the spring, elongation of a spring, and you can calculate the work done by the spring force in changing the elongation in the spring from, let's say, x1 value to x2 value. Suppose this is a vertical wall and a spring is connected here, is attached here. To one end of this wall, a spring is attached, and to the other end, a forces, external forces, stretching it, trying to stretch it. Now here you can assume that, okay, the initial separation, maybe that the initially spring is in natural length, maybe, and may not be. Maybe initially also there is some elongation in the spring. Are you getting? So suppose that already there is some elongation, and there is a force which is already acting and stressed it by some displacement x. Let's say some force is there which stressed it by some and gave it some elongation x1. And now there is a force which is acting, which is elongating it, changing its elongation from x1 to x2. And obviously this external force will also be variable, then only, are you getting?
I'm getting, sir.
It is stretching the spring slowly without imparting any kinetic energy. Now here work done will be, again you can calculate, but when we say work done, you should be very careful that whether we are calculating work done by the external force or work done by the spring force, because work is done by force. In any situation you analyze all the forces acting on the body, and then from the question try to understand very carefully that are they asking you to calculate work done by external force, or they asking you to calculate work done by the spring force. In this case we are trying to find the work done by the spring force. Now you know a spring force will have magnitude kx, and it will act opposite to the direction of the displacement. So if the displacement is in this direction, of this end, then a spring force will be in this direction. Because they are in opposite direction, that's why when we do dot product, cos 180 will come. So minus I'm taking outside kx, and displacement is, let's say, dx, and it is varying from x1 to x2. Now many students, what they do, they write a spring force as minus kx. So don't do it. You will be confused, because in dot product, the formula is fs cos theta. And in fs cos theta, f is only magnitude. Are you getting?
I'm getting, sir.
So we will only write the magnitude. We already know the direction. So that we will attach in, that will take care by theta. So if you do, you will get work done by the spring. And if you have to find work done by the spring force, then you will take the spring force. Okay. Now here you have to understand, you already know that
Sir, sir, if work is a scalar, then it should be positive, no, sir, always.
no, why? Temperature is temperature is a scalar, and it is negative temperature also, right? So negative, any quantity can have negative value. For example, potential energy is a scalar, have negative also value, right? Minus gm1 m2 by.
So like here,
Negative does not mean that it will be vector. So a scalar can have any value, positive value, zero value, negative value. But yes, here negative do not represent direction. Negative represents its actual value. So try to understand that when we say that the temperature of a room is minus 4 degrees Celsius, what we are trying to say is that its temperature is 4 degrees Celsius lower than the melting point of the ice. Are you getting?
yes, sir, I'm getting, sir.
So first we have taken the melting point of ice as a reference, like 0 degree, we defined it. And then comparing to that, we are saying that its temperature is 4 degree below that temperature, and that's why we are assigning a minus sign. Here, it has nothing to do with the direction here. Similarly, the potential energy we take as a negative, because we define zero of the potential energy when the separation is infinite. So it is based on the reference what you are taking.
So
If
like
you are
how
getting
to
minus 10 mark in an exam, then it depends on that how the calculation of zero is defined. Calculation of zero is defined that if you will not attempt any question, you will get 0 mark. Are you getting?
yes, sir, I'm getting. So
And
then why
if you
should
will
we
make a wrong attempt, then you will get a negative. Yes, tell me.
use that next one in the spring force that can explain it?
So that negative is the cos 180. Fs cos theta, cos 180. That is not about the work. That is about the, I'm saying that is about the theta, because it is the direction of force and displacement, not direction of work. Direction of force and displacement are opposite. That's why theta is 180 and cos 180 is minus 1.
Okay, sir, it's understood.
Okay. Okay. So now here, you already know that the integration, okay, there is a, you already know what is the physical meaning of integration. That when you integrate a function, suppose y is a function of x, okay, and so y is some function of x, some function of x, and then you already know that what this integration y dx represent. Similarly, you also know that what does dy by dx represent. Tell me, what does it represent, dy by dx? Suppose y is a function of x, what does dy by dx represent mathematically, geometrically?
So it means sum of adding up of areas. Small.
No, listen carefully. I'm not asking about integration. What I said is, what dy by dx differentiation
So it means
represent?
slope of a tangent at a particular point.
Yeah, so slope of tangent to the curve y as a function of x at a particular x. Similarly, here, you know that integration is nothing but addition, right? And here, if you represent integration fx dx, that is nothing but, suppose y is a function of x, and let's say I'm plotting y on y axis here and x here, and the function is represented by somewhat like this, a curve, okay, then this integration y dx will represent nothing but the summation of all fx dx. Now, summation of all fx dx, so if you take any from x1 to x2, okay, so if you take any particular strip at a position x, let's say this value is x here, at a position x, then this coordinate represents nothing but fx, right?
Yes, ma'am. Yes.
So this is nothing, this represents nothing but f of x. So for every x, there is f of x. And then, this small displacement, this small, this is nothing but dx, change in x. Okay, so this is f of x, and then f of x plus dx. So basically it represents, when you do fx dx, then fx is the length of this rectangle and dx is the width, you can say, and then it represents this area. When you integrate, you are adding all such area and you are getting complete area. So you understood that fx dx integrates, represents the area under the curve represented by y as a function of x and x-axis. Similarly here, because the work is also integration f dx or f dr, you say. So then similarly, that also represents the area under the fx curve, right? So if a fx graph is there given here, or fr graph is given here, then area under this graph will directly give you work done by the force. This method is also very popular. It can be used. Now, now to calculate work done by the graphical method, for the sake of simplicity, we have to assume the direction of force and displacement are same. But if they are not same, the graph must be plotted between f cos theta and r. This is very good. Okay, so because only you know that only f cos theta components does the work. Are you getting? And f sine theta component, its work will be 0. Why 0? Because it is always perpendicular to the displacement. So you understood that work can be negative, work can be 0, or work can be positive, depending on theta, because it is fs cos theta. So when cos theta is negative, it will be negative. Cos theta 0, it will be 0. Cos theta positive, it will be
So,
positive.
so we can say, sir, if force acting along a direction of displacement, then cos theta will not be there, no sir.
Cos theta will be there and it will be positive. Cos 0 is 1, positive.
Okay, sir. Depending on force.
So work done can be negative, can be positive, can be 0. Work done will be positive if theta is acute angle. If theta is obtuse angle, work done will be
What
negative.
is the significant meaning of positive work, sir, not negative or zero work means what, sir?
Sorry.
Sir, generally, what is the meaning of this positive work, sir? What is the significance meaning we can?
So
And
yes, you will yeah. So you will understand the significant meaning of the work when you understand the relationship between work and energy. Work and energy are related. Work is actually a way to transfer energy. So when that transfer is negative, work done is negative. For example, suppose a person is cycling and you are applying a force opposite to the direction in which he is cycling. Are you getting? So then what you are doing, what is the effect of this? That his cycle will slow down. Cycle will slow down. So by your work, you have decreased the kinetic energy of the cycle, not increased it. Are you getting? Or you can take another example. Suppose you throw a stone vertically upward. So when you throw a stone vertically upward, gravitational force is not supporting the motion. It is opposing the motion, right?
yes, sir, it is opposing the motion.
And work done by the gravitational force is negative. If you want to know what is the meaning is that whatever work the gravitational force is doing on the stone, which is moving upward, that is decreasing energy of the stone, not increasing it. And that's why we say that the work done is negative. So work is simply, you can say, a way to transfer energy. And that transfer can be positive, transfer can be negative. That's why work done positive, work done negative. For example, if you have to pay me money, so for me it is positive, for you it is negative. Means the person who is doing work, he is losing energy. Why losing energy? Because he transferred that energy to some other body. And if he is doing positive work, he is transferring positive energy. Positive energy means he is giving his energy to another body. But if he is doing negative work, he is taking out energy from that body. So work is simply, you can say that work is a mechanism by which energy can be transferred from one body to another body.
Sir, positive work means gaining of energy from another body, so you can.
So positive work, if you are doing on something, that something will gain energy. And you are doing work, so you have done the work. So when you do work, you lose energy or gain energy? You lose energy, right? Because you have used that energy to do the work. Are you getting?
Yes, sir.
See how energy is defined. What is energy?
The dot product of
No.
energy
Energy.
dot work.
Energy, not work.
Yes,
Lower
energy.
class definition of energy. What is in lower class? What is energy?
The amount of work done per unit time, you can see.
No, that is wrong. Totally wrong. Per unit time is power. That is totally wrong.
So you can say, sir, energy that is being transferred, we can see. So energy and work both are same also, then we can say.
Sorry.
So energy and work both can be same also.
No, both are not same. But if you have energy, you can do work, and if work is done, energy is transferred. So work and energy are interconnected. Means energy is defined as the capacity to do work. Are you getting?
It means capacity to do work is called energy. Understood.
Sorry.
I understood, sir.
Yeah, so energy is the capacity to do work. For example, if you have energy, because of energy, you are able to do work. Are you getting?
Yes, sir.
But when you do work, you lose energy, no? If you suppose if you do not lose energy, you will do infinite amount of work and then still you have energy left. Are you getting?
Yes, sir. I'm getting.
So whenever you are working, so energy is like a currency, like money. When you are buying something, money is going away. So when you are doing work, that currency, you are using that currency. That currency is energy. Are you getting?
I'm getting, sir.
Okay. So 1 minute. Now here you can see the units. Okay. So unit, you already know that is dot product of force and displacement. So you know that its unit will be the unit of force multiplied with unit of the displacement. Right. Unit of force multiplied with unit of the displacement. Now, what is the unit of force? Newton. What is the unit of displacement? Uh,
Meters.
meters. So, uh, yeah, its unit is Newton meter. But that Newton meter has been given a special name. We call it as we
Joule.
call it as joule. Yeah. So joule is the SI unit of the energy, and erg is the CGS unit of energy. And there is a relationship between the joule and the erg. That relationship you can also derive that using dimensional formula. One erg is simply one dyne into one dyne into centimeter. Dyne is the CGS unit of work. So the relationship is 1 joule is 10 to the power 7 erg. Energy have many different units, but SI unit is only one, which is joule, and joule is equivalent to Newton meter. Okay. Now you can try this question. See, dimensional formula of work is written. Do you know how to find dimensions?
Yes, sir. I know. No problem.
Okay, so now try this question quickly.
The position dependent forces are sort of goal.
You can just explain the process, just write the equation and that's it.
So by integrating, we can get most of this one. So by integrating force from the limits 0 to 5, we can get most.
Sorry.
So by integrating from 0 to 5, we can get most.
Yeah, integrating from 0 to 5. What you will integrate?
The force, sir. So force equation.
Okay. You will integrate force or you will integrate dot product of force and
The
the
dot product of force and direction.
okay.
FD.
So yeah, try this. You can just tell me the process or just write the equation formula. That's it. No need to do completely.
For the displacement diagram from management. As the work done and the displacement in the body. So by area, we can go upward positive, downward negative. PPT.
Yeah, so from area under the force displacement graph you can do.
Sir, upward is positive by considering science. We should consider science mostly.
Yeah, so any area downward will be negative. You will do the algebraic addition of that area. That's it. Okay, now you can try this one. Is it visible clearly?
Yes, sir. It is visible, sir. Character is written in plain object. That's fine. The figure is not visible, sir.
There is no figure. Okay. 1 minute. I will see figure. Yeah, figure is there. This is the figure. This is the question.
So means we need to find the work done by that constant force F. No, sir. Here we need to find the work done by the constant.
Yeah, calculate the work done in pulling an object with a constant force F. Yes, work done by the force F. So here you
Okay.
have to understand that when pulling word is used, no pulling, then generally the meaning is that you are sliding it without any acceleration. Means you are pulling the block so that it is just sliding without any acceleration. That is the meaning of pulling. Pulling means slowly just slide, shifting slowly. Means kinetic energy is very negligible, and the kinetic energy is negligible and acceleration, and it is constant. Means at a very slow constant speed you are moving the block. That is the meaning of word pulling.
So means acceleration should be zero. No, sir. We can access that.
Acceleration should be zero and kinetic energy should be constant. That is the same thing, because if acceleration zero, kinetic energy will be constant.
So, sir means kinetic energy should be constant and acceleration should be zero, sir. In this case, velocity should be
No
small
need
and
to say, no need to say kinetic energy. Kinetic energy, yeah. So kinetic energy will be very negligible. Like, yes,
I mean
constant,
velocity is
negligible.
very small.
You are moving it with a very slow, constant kinetic energy.
Means very slow velocity, no, sir. Small and very slow velocity.
Yeah. So velocity is very small, very slowly. It is just shifting, so negligible. इधर है ये बालकनी में थोड़ा सा पानी लीकेज का है, इसको 2 बार कंप्लेंट किया। ये यहाँ गिरता है पानी, ये पूरा फैलता है, वहां से उसका लीकेज है, और लाइट जलाएगा तो लीकेज, वहां से लीकेज ढक्कन से है, लेकिन वो यहाँ से है कि ऊपर से आता है। ऊपर से भी दिखता है वो पानी आते हुए, वो पाइप पर।
ऊपर से आता हूँ सब चेक करके।
ऊपर से एक बार देख लीजिए उसका।
लेकिन ऊपर से ही जाना।
Yes, Himanesh, you can ask. Sorry, Prabhakar, you can ask if you have any doubt.
because अपने दिमाग से यही से डिटेक्ट कर देता हूँ और ऊपर से होगा तो लाइट में है वो
अच्छा अच्छा
सब
You have any doubt? Are you there? You're not audible. Hello, Prabhakar. Hello. Am I audible, Prabhakar? You are on mute.
Hello, sir. Sir, the
Hello.
work sir,
Yes.
signal of course returning to sir, sir, we cannot find a displacement of sir in this case.
I think there's some data is missing here in this question. So let's consider the displacement is L. Yes, you cannot find the displacement.
So then, what are the we cannot find that.
And F is, suppose F is not known. So this question actually, there should be options, then you will. So option, all the options are in terms of mu only.
Some other data should be given, I think.
Yeah, length should be also given. So leave it. Actually, it so work done by the friction will be the answer. Are you getting? Mu mgl. That's it. L is, imagine that L is given. It is
Sir,
incomplete. Yeah.
sir, he's asked you to find work done with the force most.
And that is equal to work done by the friction. Mu mgl.
The force is F no, sir. Here he mentioned that F is a constant for
Yes.
support.
Force is F, and work done by the force F is same as the work done by the friction, because the kinetic energy is not changing. Are you getting? How the body will move with the zero acceleration? When F cos theta will be equal to mu mg. Are you getting?
Yes, sir.
That's why. Now try this question. Try this. It's very easy, I think. Yeah, tell me, are you getting it? Are you doing, not doing?
Sir, my favorite.
Yeah, tell me.
Sir, we need to.
What?
Sir, here, there is no need for work and work concept, no, sir.
No need. Is speak clearly. You're not. Your voice is not clearly audible.
Sir, here, work concept is not required, no, sir.
So, what is the question? If the two blocks move at a constant speed, then find the. Okay, okay, okay. So, I think that is by mistake. I think this question is okay. So, okay. So now we will go to the energy concept, and then we will do work and energy combined questions. PYQ will do. So now I'm jumping to energy, only basic energy. So energy, as you already know, it is defined as the capacity to do work. Any object having energy, it is capable of doing some work. And there are energy exists in various different forms. Energy has very important characteristics that it exists. First is it exists in many different forms, and second is that it can be transformed from one form to another form. Now, when you include all the forms of energy and add it together for a system, then it becomes the total energy, which is simply called as energy. So the energy of an isolated system remains constant. It can neither be created nor be destroyed. But here you have to understand very clearly that this energy is addition of all the forms of energy. If you are just adding mechanical energy and chemical energy of the system, suppose, and you are not adding the other energy, nuclear, electrical, sound, then you cannot say that energy remains constant. Are you getting?
So, means energy
So
means
energy of
sum
an
of all
isolated
energy.
system remains constant. So
So,
this
means energy means.
statement that I am making, that no, I- so this statement that I am making, that energy of an isolated system remains constant. In this statement, energy is all forms of energy added together, total energy. Okay. This is not about mechanical energy and not about nuclear or electrical. This is about total energy. And the statement is total energy of an isolated system remains conserved. It can neither be created nor be destroyed. But this energy is total energy. Total energy is not mechanical energy. Total energy means adding all the forms of energy together. Now, just like work, energy is also a scalar quantity, and its unit is also same as energy. So its SI unit is also joule. Okay. Now, the two forms of energy that we will be discussing in this whole chapter mostly is the mechanical energy. We are mostly in mechanics part concerned with mechanical energy, and mechanical energy is nothing but sum total of kinetic energy and potential energy of a system. But before going into mechanical energy, let's talk about what is kinetic and what is potential. I think kinetic energy you already know. This is the energy possessed by a body by virtue of its motion. Means if a body is in motion, then only it will have this form of energy, and that is due to its motion. Now here you have to understand that because kinetic energy is a frame dependent quantity. So the same object can have different kinetic energy in different frame of reference.
Sir, due to motion, a body gains some energy, sir. That is called kinetic energy, sir, here.
Means first what you are trying to say is not correct. It's not that due to motion it gains, means first there is motion and then it gains something. No, it is due to motion. So due to motion, not it gains due to motion, means it is the same thing that you are saying, but the meaning, you have to understand that the moment motion is there, kinetic energy is there. It's not that motion is there and then it will start gaining some energy. Not like that. Motion is there, kinetic energy is there.
Sir, if velocity is varying, then kinetic energy is how we can define, sir?
Kinetic energy is
Integration
varying. Varying.
means if velocity is varying, sir.
No, not velocity varying. So it is due to motion. And yeah, so now I'm coming to the mathematical part. But here you have to understand that the velocity is varying. Then also it is moving. No, body is moving, moving. So it will have kinetic energy.
Sir, if finally it comes to rest, sir,
Then
that's
it
going
zero
on the
zero comes to rest. So then no energy.
sir, then means this energy is taken. This energy is
Yes.
taken by the friction we can take, sir.
Not by
This
friction, by any other force. Why
sir,
only
there is no.
friction? There may be some other force also, no? Who is bringing the body to rest? Some other external force, a spring force, anything.
Yes, sir. Okay, sir.
So this energy is due to motion. So if motion is there, energy is there. Motion is not there, energy is not there. And so the only situation in which kinetic energy will become zero is when there is no motion. But then you have to understand that motion is a frame dependent quantity. It depends on frame of reference. And that's why the same body can have different kinetic energy in different frame of reference. And it can have zero kinetic energy also in some other frame of reference. For example, you are sitting in a car and then kinetic energy of car with respect to the car frame becomes zero. So it is a frame dependent physical quantity, and mathematically it is defined as half mv square, where m is mass and v is a speed. Kinetic energy, as you can see from the formula, it cannot be negative because the mass is positive and v square is also positive. So kinetic energy is always positive. Kinetic energy cannot be negative, but it can be zero. If there is no motion, there is. Can also be defined in terms of momentum. Momentum will also come whenever there is motion. So if there is motion, definitely momentum will be there. It can also be expressed in terms of the magnitude of momentum, that p square by 2m. You have any doubt in this topic, you can ask.
Sir, I mean, sir, if sir, from where the body is gaining this energy, sir?
So tell me one thing, why you are thinking that it has to gain energies from somewhere?
Sir, because energies cannot be created, no, sir.
So
It
it is
should
not
be.
created. Who told you it is created? When it is created, tell me. A body is moving, it has energy. Has energy, not it. Energy can neither be created, but 1 minute.
Okay, sir.
ये 107 है. वो. हाँ. Yeah, so energy can neither be created nor be destroyed. Are you getting? But but energy energy creation and है ना, and you cannot destroy, but energy is there no already. So if a body is moving with a uniform kinetic energy, it has energy, and energy is है ना.
Sometimes the meaning of this means, sir, if you say that
Meaning
if
of this
kinetic
is
energy,
meaning of this is that the energy of a system will remain constant. Energy can neither be created nor be destroyed means energy remains constant. And if the body is moving with a uniform kinetic energy, its energy is constant. So no, not created, not destroyed.
sir, sir means if we say that if energy is half mv square, sir, if the body is moving, we're saying that the body is having this energy, no, sir.
Yes.
If we are saying that if this is not created, sir, then the body should have this energy, no, sir. Whether it is at rest also.
Yeah. So the body have energy and the body is moving and body will keep moving according to Newton's first law. So it will not lose energy. A body is moving, who will stop it? It will keep moving, no? And it will keep moving, so it will have that energy will neither increase nor decrease. Now you come to the main point and ask the main question.
Sir, main doubt I'm not getting is, sir, if this energy coming immediately after the motion starts, no, sir, as the motion starts.
Now you are asking the correct question. When you say motion is starting, then yes, is starting. So can anything start without any work?
No, sir, it cannot start.
So then some external person is doing work. And I already told you work is a mechanism to transfer energy. So that mechanism transferred that energy.
And that force done by that work is this kinetic energy, you can say, sir.
And that work is not this kinetic energy. That work is equal to change in kinetic energy. Because the body can have kinetic energy initially also, no? That is also possible, no? Are you getting?
Yes, sir, it is possible, sir. It is.
So a body moving with constant kinetic energy, no need to acquire it any kind. It already have that energy. Yeah, the point of gaining energy or losing energy comes when you say that it is started or it coming to rest. Then only. Even for changing direction, no work is required. And that's why even if the direction is changing, then also no kinetic energy is not changing. Are you getting? Kinetic energy has to do with work, not with force directly. Are you getting? Because if a particle is moving in a circle, force is acting, but kinetic energy not changing. Are you getting? Force cannot change kinetic energy. Work can change.
Yes, okay, sir. Means kinetic energy is related to work, we can say.
No. Kinetic energy is not related to work. Means, yeah. So if you are saying that, yeah. So, but the thing is that you are saying kinetic energy is related to work because you think that something has to come from rest to a particular velocity, right?
Yes, sir.
And
Some
that
rest
is
it is
that
coming to a
is wrong. That is wrong. That is what the Galileo understood first time, that rest is not the natural state. You are not able to imagine that something can be already moving. You are not able to imagine that because you don't see around yourself. Are you getting? Around yourself, you see things starting from rest, and then you see things coming to rest. Are you getting? You never saw something which is moving and continuously moving and never stopping. But there are things in the universe, na? Are you getting?
Yes, sir, I'm getting, sir.
Which is already moving and moving and for millions year moving and will keep moving and will keep moving because Newton's law allows it. So rest is not the natural state. The uniform motion is equally natural state as the rest is. A body can stay in the rest, and a body can stay moving with uniform velocity, and both are equally possible. You don't see around yourself, and that's why you think that okay, something has to come from rest to a particular velocity, so some work is required. But then there are things which are continuously moving, and no work is required because they already they are moving from the big bang itself, and Newton's law allows it, no?
So, but we said that if from frame independent, no, sir, you said
It is
work
frame
for it.
dependent, frame
So, then,
dependent.
so frame dependent. Then, if you change the frame of references, the body may be in rest also, no, sir. Some
Yes,
case.
it will be in rest. Yes, everybody will be in rest. Everybody in its own frame. So, what is the problem that I'm asking? It will be in rest. So, what? What is the problem?
Yes, understood, Matra, no.
Okay. So now you can try this question. Okay, now try this question.
Sir, which question, sir?
Question is not visible to you on a screen.
Sir, not visible, sir.
Okay, 1 minute. Still not visible.
Sir, not visible, sir. Still.
Okay, 1 minute.